Okay, so welcome to multivariable calculus. This is lecture 9. And so we're going to be doing today is we're going to be talking about vectors. There's a lot of properties about vectors in the book. We're not going to go through every single one of them. Most of them, fortunately, are commonsensical. One of the things you have to be a little bit careful about is different books, different classes will use slightly different notation. The book, I think, remarks that they will try to use angular brackets for vectors. They will try to use parentheses for points, but a lot of places just use parentheses for both. So just always be aware of what you're reading and what language and notation they choose to use. Okay, so who here has seen Despicable Me? All right, what's the definition of vector? Oh, yes, why does he call himself vector? Magnitude and direction, right? I don't know if that movie is old enough so that this might have been your first encounter of the word vector. So for us, vectors have magnitudes and directors. So magnitude and direction. And so normally what we'll do is we will frequently work in R3 or Rn. So R3 is the set of all points x, y, z. X, y, and z are real numbers. More generally, of course, we could work in n-dimensional space. Is it really that much harder to work in n-dimensional space? If you're doing things abstractly and formally, no. You just have more things, after the comma. If you want to build a physical model and look at it, however, yes, it's much harder once you start working in 4, 5, 6-dimensional space. So I was hearing some physics talk. You might look at configuration space at some point, in which case for a specific particle, you might have its 3 position coordinates and its 3 momentum coordinates. You might actually have a 6-dimensional object to describe the trajectory of a particle over time, not just where it is, but how fast does it travel. So that's going to be hard to visualize a 6-dimensional thing. There are different games and tricks we can do. Sometimes if you want to try to visualize, something 4-dimensional, you might try to use, color. And, different colors could give you some sense about, maybe the magnitude of something at a given point. Normally, we will write things as, V with an arrow over it for a vector. A lot of times people use what's called math blackboard or boldface. If you notice, I'm writing the R with an extra line over there. Sometimes people like to put vectors in bold notation. When you're writing in a textbook, it's very easy to just put in, okay, now just put this in bold. If I'm doing this on the notes like this, do you really want me spending my time going like this? Versus, I think it's just much easier to just put an arrow over to remind myself that this is a vector so I can quickly look down and see V is a vector. But a lot of times in books, they won't do the arrow. They'll just write it in bold like this. There are certain vectors that are more convenient than others. If you answer this incorrectly, you can flunk the class. This is one of the few questions. What does New York City or a specific subset of New York City do better than Boston? Nothing is not a bad answer, but there is one part of New York City that does something much better than Boston. The grid where? Downtown in Manhattan, it's really nice in the grid there. You've got your north-south, you've got your east-west. And it's very easy to describe where you are. So there's a natural set of directions. If you're trying to describe how to get somewhere in Manhattan and you don't really talk about going, east, west, north, south, you're an idiot. Go so many blocks east, go so many blocks north. Boston, you've got roads crossing each other. And it's a lot more interesting to get around. So in a situation like this, it's very natural to use the coordinate grid, and we have some preferred directions. You hopefully have been traumatized at some point in your life about finding the equations of ellipses. If I give you, an ellipse like this, aligned with the coordinate axes, and I have A over here and B over here, this is x over A squared plus y over B squared equals 1. Well, what if, instead of giving you an ellipse like this, I give you instead an ellipse like this. And so now, if I look at it like this, it's a little bit harder. How many of you remember how to write down the equation of an ellipse like this? It's often not done in high school. It's actually really easy in linear algebra if you just change your perspective. It's basically saying, well, look, why not use this new coordinate system, UV? And in this new UV system, I understand how to write it down because it's now aligned perfectly with that. And then I just need a way to convert back and forth between the UV space and the XY space. So if you continue in math, the next natural course to take is linear algebra. So much of linear algebra is just converting from one coordinate system to another. Depending on what your problem is, some coordinate systems will be more natural than others. We're going to do three big ones in this class. We're going to do polar, which hopefully you've seen in high school. This is the r and theta. And then the other ones, it's really hard to hide what they're for. Anybody want to guess what cylindrical coordinates are good for? Cylinders, right. And in a shock, spherical coordinates? Spheres, right? These are the really good ones for a lot of problems. A lot of problems have spherical or cylindrical or circular symmetry. And so it's nice to have coordinates that take advantage of that. In general, if you have a nice Cartesian grid, we often want our directions to be perpendicular. So we'll often do east, west, north, south. And if we go three directions, we'll go up, down. But if you continue to linear algebra, you actually learn about how to handle a lot of other different coordinate systems. All right, so then there's a bunch of notations. And so we can let E1 would be the vector 1, 0, 0, and there's however many components we have. E2 would be 0, 1, 0, and so on, all the way down to En would be 0, 0, 0, dot, 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 0, 1. This is really good notation. And it allows me to handle an arbitrary number of coordinates. If I have 15 coordinates, if I have 20 coordinates, it just changes the value of n. We also use I hat to be the vector 1, 0, 0, j hat to be 0, 1, 0. And what do you think the last one is? What would you guess? Okay. Now we could continue to go on if we want to do things in 4 dimensions, I, J, K. We could do L hat. At this point, we basically just use the E's. And E is coming from Euclidean space. So E for Euclidean space, say. This is the standard geometry you've seen before. You were looking in n-dimensional space, like R. Disadvantages and disadvantages using IJK. If you just quickly look down at it, you can say, okay, this is essentially my X direction, my Y direction, my Z direction. But if I want to add more directions, if I want to go in a higher dimensional space, I start running out of letters in the alphabet. And that's why the E's are better, because it doesn't matter how many dimensions I have, I can just have more and more components like this. The hat vector. But that means it has length 1. And so the big question is, how do we calculate the length of a vector? Well, if I give you a vector, let's start off in the plane. I have to give you a base point, and then I give you a direction. And then I'll have maybe my terminal point over here. So maybe my base point is maybe 2, 1, and maybe my terminal point is maybe 4, 5. And so the vector is, I'll do it this way, 4 minus 2, 5 minus 1. And so that would be the vector 2, 4. What is another natural base point to use for vectors? So I'm here, I'm drawing a vector starting at the point 2, 1. Where would be another natural point to have as my base point? Yeah, 0, 0. We could always have this as my base point. Oops. And so what I could do is I could redraw this. And here's my 2 points. And I could, here's my first one, here's my second one. And so from the first one, I would get 2, 1. From the second one, I would get 4, 5. I want to use angular brackets. And if I subtract it like that, that would give me the vector 2, 4, same as before. And again, for a lot of things, if they don't say anything, just assume that the vector is based at the origin. But depending on what you're doing, you might want to have your vector living at another place. So when we talk about a vector, we have magnitude and direction. We might also want to care about where is it happening? Where's the point of interest? I can talk about just more generally, I have a vector in this direction. I want to talk about moving in this direction. Bless you. But I might care about where is this happening? If I have a particle, I might be concerned, what's the force on that particle? Well, I've got the direction of the force, I've got the magnitude of the force, and then I also have the point in space where the force is acting. And so it's a question of just how much information do you want to include in all of this study? Bless you. So I can just give you 2, 4, that's a vector. I move over 2 units in the x direction, I move up 4 units in the y direction. And I can also tell you where is it anchored. And then the next question is, what are properties of vectors? So essentially, any property you want the vectors to have that's reasonable, the vectors have. Okay, so vectors have nice properties. I'll just list a couple of them. And so here, I'll do it this way, U, V, and W are vectors, and then A and B are scalars. For us, that's mostly going to be real, or sometimes we might want to use complex numbers. So if you've ever tried to solve a polynomial, you quickly learn that a lot of polynomials don't have roots like you would like. If I give you a polynomial with integer coefficients, does it have to have an integer root? So can you give me a polynomial with integer coefficients that doesn't have an integer root? Yes. Okay, but that's way too complicated. Can you give me a degree 1 polynomial with integer coefficients that doesn't have an integer root? Give me the simplest example you can think of. So if I try it like, x minus 5 equals 0, okay, that has a root of 5. If I try x minus 7 equals 0, okay, that has the root of 7. Can somebody give me a polynomial which has integer coefficients but not integer roots? I'm sorry? Well, I want something just of x. Well, you have to give me an equation. So if I give you x minus 5 equals 0, the root is 5. If I give you x minus 7 equals 0, the root is 7. Can you give me something where the root is not an integer? Okay, but let's try to keep it to just degree 1. So x minus 5, x minus 7, x plus 11, these don't work. So you have to make it a little bit more complicated. How could you make it a little bit more complicated than x minus 5? Still keep it as a degree 1 polynomial. What could you try? So give me something, just try a polynomial. X minus 5, x minus 7, x plus 11, these are all too simple. What can we change? Okay, but now you made it degree 2. Keep it degree 1. I'm sorry? Okay, but now, you're close, but that doesn't have integer coefficients. X minus 5/3 has the root of 5/3. That's good. That's our first example that doesn't have an integer root. But now it doesn't have integer coefficients. What is similar to x minus 5/3? Sure, so if we do something like 2x minus 5 equals 0, or if we do 3x minus 5 equals 0, that will have roots, 5/3 or stuff like that. So we see that just because a polynomial has integer coefficients, it doesn't have to have integer roots. But we still saw that, hey, it has polynomial roots. I'm sorry, it has rational roots, So maybe if you have rational coefficients, you have rational roots. And we can try a more complicated thing, and we do x squared minus 2 equals 0. Oh, crap. That has integer coefficients, it has rational coefficients, but the root is irrational. It's the square root of 2. So then you go, well, maybe if you have real coefficients, you have real roots. Then we do x squared plus 1 equals 0, and we get, oh, the root is the square root of -1, which we call I, not to be confused with the I which we have just so happily introduced a moment ago. It turns out once you add the square root of -1, any polynomial with complex coefficients has only complex roots. You don't have to add anything more than I. And so when we're trying to solve things, sometimes the real numbers just aren't enough. And that's why sometimes we'll be doing things over the complex numbers, because not all polynomials with real coefficients always have real answers, always have real solutions. For the most part, we'll be working with real numbers, but we might occasionally want to extend. And so what properties would we want vectors to have? Well, the first one is AV is same direction as V and A times as far. If A is negative, it is 180 degrees other direction. So for example, if I take V to be 1, 2, here's V, and if I take A to be 3, here would be 3 times V. It's the same direction, but going 3 times as far. If I took A to be -1, here would be negative V. It's the same direction, but going in the just flipped. Right? So this is the first natural thing we would hope to have, right? Next is, V plus W. This is the parallelogram rule. So if I give you, here's V, and here's W, what I can do is I can first move V, and then I can add up W. Turn it a little bit better. And then this new thing over here would be my V plus W. So what I've really done over here is I've just slid W along V. So I've got the same vector as before. I've just changed where its base point is. I first move V, and then I move W. And I can use the parallelogram rule to add. What would you hope V plus W also equals? Yes, and it turns out this is the same as W plus V. And so just going in the other direction, I could slide V so that first I move W, and then I walk in the direction of V from W. So this that the order doesn't matter. I can add V then W or W then V. If you've done matrices, with matrices, it actually matters the order in which you multiply matrices in general. For a lot of things in life, does it matter the order in which you do things? So at some point when we finish this chapter, we'll have a test. So you can study and then take the test, or you can take the test and then study. Yes. I don't. It really depends on, think of it as, within a few days after we finish this chapter will be the test. So do you think it matters the order in which you do these things? Study, then test versus test, then study. Yeah, most things in life, order is going to matter. It's nice when the order doesn't matter and you can be a little bit free. Oh, okay, whichever one is more convenient, I'll do that one first and then I'll do the other. Anybody know any other nice properties we have of numbers that we might hope carries on? We just did commutativity. What else might you hope? So what other nice properties do numbers have? There's two other good ones. So basically, instead of doing adding, we could do subtracting. And that's basically just using what we had a moment ago, that if we multiply by -1, we're just flipping the direction. So we could do, v minus w is just v plus -1 times w. Good. What else could we have? What other properties do you want integers to have when you're adding them? So one is commutativity. What else do we have? What if I give you 3 vectors? What is v? Well, let's do it as u plus v plus w. What does that mean? When you say u plus v plus w, what does this mean? Yes. We're not 3 different dimensions, 3 different vectors. But what does it mean when I say u plus v plus w? What should I do? How do I add them? I can only add 2 at a time. Yes. Okay, but which 2 do I add first? It doesn't matter. So this is associativity. This is u plus v plus w, or u plus v plus w. So this is called associativity. I'm sorry?
You can add values from different vectors together.
Right, so the way you would add vectors is, we've talked about the parallelogram rule. If I have 2 vectors, v and w, to get v plus w, I would just add them like this. And so the parallelogram tells me how to add 2 vectors. But what if I wanted to add 3 vectors? Well, I add 2 of them, and then that gives me a new vector. U plus v is now just a new vector. And I take that new vector and I use the parallelogram rule and I add w. Because it doesn't matter, because they give you the same answer, we are often lazy and we drop the parentheses and we say, let's just add u plus v plus w. Don't overload by putting too much down. Okay. Is there a question on this?
I was just confused because like this type of
you can add them. It just gives you a new vector that's, so if I give you, for example, say 1 0 0, 0 1 0, and 0 0 1, then if I do this as u, v, and w, u plus v, sorry, we're supposed to use, no, I'll try to remember to use, this is just going to be the vector 1 1 0. So u plus v plus w would be 1 1 0 plus 0 0 1, which would be 1 1 1. Yes.
So that's like, what does that mean physically?
Basically, it means the parallelogram rule is that I first move in the direction of v, and then starting at the endpoint of v, I now move in the direction of w. So w is giving me a direction, and it's giving me a magnitude in that direction. It's telling me how far to move in that direction. And so if I give you as 2 vectors, 1 4 8, it is hard for me because I grew up with just often not using the angular brackets. And 2 -3 7, let's not make it 7, let's make it 8, because the 7 is going to look too close to an angular bracket. Then 1 4 8 plus 2 -3 8 is you just add component by component. So it'll be 3 1 16. So if I want to figure out what is the effect of one vector with another one added, I just add component by component. What am I really doing? I'm really using the parallelogram rule. If I want to figure out what is v plus w, well, I start at my base point and I go in the direction of v and I go its length. And then I stop and that's my v. And now to this, I want to add w. So starting where I ended, I now add w and I end up at that new point, which I'm going to call v plus w. And so if you look at the net effect of where I ended, that's the red vector. I started here, I ended here. I could have also gotten there by going the other way. It's like, I have two ways of walking to something. If I want to get from here to the corner over there, I could walk like this in that way. Or if I start here, I could also walk like this. I get to the same point. I'm just going two different paths to get there. And what's really nice about the vectors is v plus w is the same as w plus v. It doesn't matter the order in which I add them. And if you can look at the examples we've just done, the way we define vector addition is we're adding components. Well, normal addition is commutative. Normal addition doesn't really matter which order you add the numbers. And that's why we have this commutativity. Because if I do, v plus w, that would be v1, v2, ... vn plus w1, w2, ... wn. I now add component by component. I'll get v1 plus w1, ... all the way up to vn plus wn. But now I use commutativity of addition. And for each of these components, normal commutativity. But now that's the same as w1, wn plus v1, vn, which is the same as w plus v. So this would be a proof of the commutativity of addition of vectors. And it's really just inheriting it from the commutativity of numbers. Because normal addition is commutative, when I add component by component, I've got w1 plus v1, I can flip that to v1 plus w1. Or if I'm at v1 plus w1, I can flip that to w1 plus v1. And I just do it component by component by component. This is where you get associativity. Normal addition is associative. And so when you go through this argument, you'll get this. There's another property. We have associativity, we have commutativity. Does anybody remember anything else from numbers? This would be property 5. Yes. I'm sorry? So transitivity would be, that's more for relations. V is less than, and so it's not a bad thing to try, but we don't really have the less than here. Because one of the problems is as you keep going around the circle, you eventually come back to where you started. And so you could actually say you're less than yourself, which does cause trouble in complex analysis. There's another property though that normal addition or normal numbers have, but it doesn't use just addition, it uses addition and multiplication. Okay, so not quite order. The distributive property. So we have A of V plus W is equal to AV plus AW. If you think about it, I can first add V and W and then rescale by a factor of A, or I can rescale V, rescale W, and then add them. And again, the way you would prove this is you would just go through and do a calculation very similar to this. So as a nice exercise, if you want, just try to go through and prove that the distributive law holds. All right, so these are your basic properties of vectors. We have special vectors. Anybody want to guess what the most important special vector is? So it's the 0 vector. And it has the wonderful property that 0 plus v is v plus 0 is what? Not 0. So we take v and add 0 to it. What should we get? We should get back. Okay, we should get back 0 plus v. But if I take a vector and I add 0 to it, what should I get? I should just get back v. So this should basically not change anything. If you look at how much money you have in your bank account, and then out of the goodness of my heart, I deposit $0 in your account. And I do that, and I'm going to do this for all students in all of my classes this semester. You're welcome. There's no net change. So this is a really important vector. Similarly, if I multiply a vector by 1, what should be the effect? No change. Okay, so one of the things we've talked a little bit about is the length of a vector. So how do we find length of a vector? So we use one of the most important things, the Pythagorean formula. Given that we're at Williams College, who was the greatest president of all time in US history? Garfield, right? But it's not because he became president. It's not because he was assassinated on the way to, I think, his 25th reunion. It's because he is credited with a proof of the Pythagorean theorem. He is actually credited with one. Because this is being recorded and I teach at Williams, I will not talk about whether or not his proof is highly, highly, highly derivative of a standard one, but he is given credit, right? So the only real freedom you have in something like this is which way you draw the triangle and which sides you call A, B, and C. And so the Pythagorean formula is if you have a right triangle, a squared plus b squared equals c squared. There's the more general law of cosines, which we will get to later. And so the question is, how do you prove this? So there's a lot of different proofs. At some point in the semester, I might actually give an entire lecture on how to prove this. This is so important. My favorite, which I saw in my freshman physics class, was the following. See if I can just draw it correctly. And then everybody is supposed to use their imagination that these are drawn correctly. Okay, good. And so this is going to be A, this is B, this is A, this is B, A, B, A, B. And again, we are being very generous in considering that I drew a square, okay? Oops, didn't change color. I'm now going to connect these. I'm going to form 4 triangles. Okay, so I've got 4 copies of my original triangle. The shape may not look like it, but what shape did I just draw in blue? A square. So with a little bit of exercise, you can actually show that these are all right angles. So I'm going to assume a couple of facts. I'm going to assume we know the area of a rectangle. So if I give you a rectangle that's x by y, the area is xy. And if I give you a right triangle that's x and y, the area is 1/2 xy, because it's just half the area of the rectangle. So I'm going to assume these are given, that I know this. If we have to go all the way back and prove everything from geometry onward, we are not going to get to multivariable calculus. So I'm going to assume we understand that the area of a rectangle that's x by y is xy, that the area of a right triangle is 1/2 xy. What is the area of the big black triangle? And big square, sorry. Big square is a plus b squared. Little square is what? So what would the little square be? C squared. each triangle is what? So if I give you each of these triangles, what's the area of this triangle? Good, it's 1/2 A times B. So A plus B squared equals C squared plus 4 times 1/2 AB, right? I've just calculated the area two different ways. This is one of the big things we do in mathematics. We calculate areas two different ways. We calculate some quantity two different ways. Well, if I square out A plus B squared, I get A squared plus 2AB plus B squared is C squared plus 2AB. I cancel the 2ABs, and there's the Pythagorean formula. Okay, so we now have a way to calculate the length of a vector in the plane. So length in the plane. So if I give you some vector like this, I can write, here's my X component, here's my Y component. And so my length would just be, if this is 0, 0 here, and this is XY, the length is X squared plus Y squared square root. So the Pythagorean formula is essential for giving us length. Just the point 0, 0. Just basing things at 0, 0 to make it simple. So this is how we calculate the length of a vector in a plane. And what we might do is we might say if V is the vector xy, then either double V or just 1V is the square root of X squared plus Y squared. I like to use the double V and the arrow to just really emphasize I'm talking about a vector here. But in some sense, what we could do is we could just say, you know what, when we first learned the absolute value, we did the absolute value for real numbers. And if it was a positive number, the absolute value was just the number. If it was a negative number, it was the negative of that. And then we might have generalized the absolute value for complex numbers. If I give you A plus IB, the absolute value would be the square root of A squared plus B squared. That's essentially what's going on here. And you can say, why not just generalize the notion of absolute value to give us this non-negative quantity, which is the length or the magnitude? And let's extend that to vectors. So when I talk about the absolute value of the vector V, I just mean its length or magnitude. That's a perfectly legitimate extension of the absolute value. It's notation. Notation is meant to help. And this way we can use the absolute value not just on real numbers, not just on complex numbers, but we can also use it on a vector. Or we could say, you know what, I don't really want to confuse myself, and I'm going to use double lines to just remind myself that I'm working with a vector. Either one is fine. So then the question is, what would happen if we had a vector in 3 space? This is where it would be nice if I could actually draw. So let's say we have something like this. Here's my X direction, here's my Y direction, here's my Z direction. And I've got some vector coming out like this. Well, what I can do is, we talked a little bit about this earlier in the day, foreshadowing, is I can try to write it as the sum of 2 vectors, where one vector is in the XY plane, and then the other one is going just straight up in the Z direction. And then I can represent the length. So if I call this vector V, I can call this I'll call this vector VZ because it's just in the Z direction. And I can call this VXY because it's in the XY plane. And basically I would get that the length of V squared is the length of VZ squared plus the length of VXY squared. just using Pythagoras applied to those two different directions. And now I zoom in to the xy plane. And here's my vector vxy. And I can write it as, say, vx and vy. So this part here would equal the length of vx squared plus the length of vy squared. So putting all together, if v is x, y, z, we would get the length of v is the square root of x squared plus y squared plus z squared. And the way we get it is we just used Pythagoras twice. So 3 space, Pythagoras twice. What do you think would happen if we were in 4 space? Pythagoras 3 times. Yes. I'm sorry? The double lines is just the length. So this is notation for the length. You can use either double lines or single lines. Some people don't like using single lines because the absolute value was defined initially just for real numbers. Otherwise, it's like, well, why not just extend our definition? And it's going to be more useful to be able to talk about the absolute value. What do we mean by absolute value? We mean, in some sense, the length or the magnitude. I like to put in the double lines to just really highlight the fact that I'm talking about a vector here and never forget that I'm talking about a vector. So in general, if I give you, v is x1 through xn, then the length of v would just be the square root of x1 squared plus xn squared. And this just follows from multiple applications of Pythagoras. Okay, so one of the most important concepts in calculus is the equation of a line. And so we have a lot of ways that we've done it. So if I give you, things in one dimension, and here is my line, y could be, mx plus b is a common way of writing this. And so we might do, sorry. So this is slope intercept. So m is the slope and b is the y-intercept. Could also do point slope. So I give you slope is m, I give you a point, say x naught, y naught, then you get y minus y naught is m x minus x naught. Or y equals y naught plus m x minus x naught. I could also give you, 2 points, because 2 points determine a line. But if I give you 2 points, then I get the slope is y1 minus y0 over x1 minus x0. Now use this. So if I give you 2 points, well, just calculate the slope, and now you're in the position where you have the slope and a point. So the question is, how does this notion of a line generalize to higher dimensions? So again, we're seeing that there's multiple ways of writing down the equation of a line. Depending on what information I give you, I can write it down in slightly different ways. I can write it as y equals mx plus b. What's nice about that is I can quickly look at that and see where's the slope. I can see where's the intercept. What's nice about this is if the action is happening at the point x naught, well, when x equals x naught, my value is y naught. And if I move just a little bit from x naught, this tells me by how much I changed. So this looks like this is going to be great for calculus. Okay, so now let's look at other ways. So lines in higher dimension. So what I'm really going to do is I'm going to have a point P. Let's do x naught, y naught, z naught. We'll do it in 3 dimensions, but you could do it more generally. And a direction V. So if you think about what's going on, I want some line in space. I have some point here, P. I have some direction, V. And then all the points in the line, coming from my origin, it's got to be equivalent to just starting at P and moving some direction along that line. It's going to be all points of the form P plus T times V. And so what we might do is we might write this as, let me call that P naught for my initial point. And I'll call this my new point P is going to be of some form like this. I might put a little subscript T, so T is a real number, and different values of T will give me different points on the line. When T equals 0, I'm going to just be at P naught. When T equals 1, I go P naught and I just move 1 unit of V. If T equals 2, I move 2 units of V. If T equals -1, I move back 1 unit of V. So we could write this as, x of t, y of t, z of t is x naught, y naught, z naught plus t vx, vy, vz, or x of t equals x naught plus t vx, y of t is y naught plus t vy, z of t is z naught plus t vz. So I start at a fixed spot, and this tells me how much I move. A line is a one-dimensional object.
Why is there an arrow over the P? Like, is it?
Oh, yeah. It's a point, but it's also a vector coming from the origin to where you are on the line.
Okay.
And so I often abuse notation a little bit and just, it is a point, but and this is why the book sometimes say, we sometimes use the same notation for point and vector. It is a point, but we're adding vectors to it. So it really is a vector coming from the origin to there. So when you see this, the new point P is P naught plus TV, what does this remind you of? Which of the equations of a line? Yeah, it looks a lot like y equals mx plus b. So there's different ways of writing things. In some sense, is vx, vy, vz essentially the same as a slope? So let's look at what's going on in 1 dimension, in 2 dimensions in a plane. So let's say, I have my line. This is y equals mx plus b. And let's say I have some point here, x naught, y naught. And now I move over 1 unit in x, and I see how much I move down in y. And that gives me my slope. So the slope is the change in y over the change in x. It's y minus y naught over x minus x naught. Okay. I can write this as a vector. If I move x by 1, how much does y change? It changes by the slope. So if I want to write things as, y minus y naught equals m x minus x naught, there's a lot of similarity between this and what we were just doing a moment ago. It's how do we generalize this notion of a slope? When I talk about the slope, it's I move x 1 unit and this is how much things change. We have to be a little bit careful because what if the slope is 0 or infinity? We have some issues with that. All right, so the homework for today's Friday, I guess for Monday, and these are always on the web page. These are also in the slides, which I will post, is do the problems from section 12.1 and 12.2. If there are any things that we've gone through that you want me to cover in greater detail in class, just let me know and we'll spend some more time on that on Monday. And then we will just continue going through with chapter 12. All right, so this is a good place to stop.